In this final tutorial of equilibrium, I want to talk about reaction quotient, which is same expression as Kc, equilibrium constant, but this time you use initial concentrations rather than equilibrium concentrations. Now, there are three possibilities. If Q is equal to Kc, you are at equilibrium, there is no net change in reactants or products. Their concentration remains the same. Now, if Q happens to be bigger than Kc, you have to come back from right to left. So you are going from products rather toward reactants in order to reach equilibrium. The last case is if Q is less than Kc, as you calculate plugging initial concentrations, that means you are going toward products. You are going from reactants toward products. So the system is not at equilibrium and you are going in that direction. Now let's look at a typical question that a few years ago was given in IB. You have 2 moles of NO2 and 2 moles of N2O4 in a reaction vessel. The temperature is 320. The vessel is closed. Equilibrium is reached. And the question is, would you have more than 2 moles of NO2 or less? So initial is 2 of this and 2 of this. And the question is finally at equilibrium, how much of NO2 do you have? So I write reaction quotient rather than Kc. So Qc is simply same expression, products, concentration of products, raised to its coefficient, which is 1, divided by concentration of reactants, raised to its coefficient, which is 2. Now, since it's 1 dm cube vessel, your moles and concentration are the same. So this is 2 mole per decimeter cube, and this is 2 mole per decimeter cube. So let's just plug it in. So initially I have 2 divided by 2 squared, which is 2 divided by 4, which is 1 divided by 2, and it's 0.5. Now this is a case that Kc is 1 and Qc, so Qc is less than K. So what you're trying to do is go from reactants to products. So you still haven't reached equilibrium. This is a case that reactants are going toward products. It makes sense. You want the numerator, which is product, to get bigger and denominator, which is reactant, to decrease. So eventually, once your equilibrium is reached, you're definitely less than 2 mole per decimeter cube or 2 moles. So equilibrium concentration of NO2 will be less than 2 at equilibrium. So this is reaction quotient and its application, which is same concept as K, just plug it in, except use initial concentrations in order to make a judgment and see where you are in contrast to equilibrium position. Now the very last thing I want to do is this reaction, talk about it a little bit. NO2 is a sort of a brown gas and N2O4 is colorless. Now if you increase pressure due to Le Chatelier, you go to the side with less number of moles, which is you become more colorless. Now this question is saying at 320 it's a yellow vessel. So this reaction is yellow at 320. Now when temperature is increased to 375 Kelvin, it becomes darker brown. You don't see the last word color. Now using Le Chatelier, is this reaction exo or endo? So as temperature is increasing from 320 to 375, you are really becoming more brown. So you are shifting toward reactants. Now, where is the case that you shift toward reactants? If this was your reactant and product, definitely the heat should be a quantity on the product side, because as you increase temperature, you're shifting this side. And then by definition, if heat is on the product side, this means you are exothermic reaction. So this is exothermic reaction. Now, would Kc change, and would it be bigger than 1 or lesser than 1? So Kc at 375 degree Kelvin, since you are going to, this is ratio of products over reactant, since you are producing more of the brown color, this is going up, this is going down. So as you increase temperature for exothermic reaction, Kc gets smaller, so Kc is less than 1. So this was my final touches on equilibrium. I wish you good luck.